In section 8.4, we're going to be testing a claim about a mean. We're going to use the p-value method in some cases and the critical value method in other cases. So this section is very similar to the previous section 8.3, except instead of testing a claim about a proportion, we're testing claims about means. But most of the stuff we talk about should seem very familiar if you just did section 8.3. That is, all the steps will be the same. The main difference between the two sections is when we're testing a claim about a mean, we have to use a different test statistic. That test statistic is going to have a different distribution, namely the t-distribution that we've seen before. But otherwise, it's a very similar idea behind each of these problems we'll go over. So let's start with the test statistic in this section we're going to use is, as I mentioned, going to be something that follows a t-distribution, and that is our sample mean minus the population mean that we're assuming, and this will again be based on what we say in our null hypothesis, divided by the sample standard deviation, which is itself divided by the square root of our sample size. And this we're calling t because it's going to follow the t-distribution instead of the normal distribution that we use for proportions. And just to be sure, we'll use this test statistic for either method, the p-value method or the critical value method. So for the p-value, again, this is the probability of getting a test statistic at least as extreme as our test statistic. So it'll, again, be very similar to what we looked at before. It's just now, instead of talking about the normal distribution, we are talking about the t-distribution. So we'll need to look up p-values on our t-distribution table. So let's take a look at this example. A boat company claims that the mean weight of men is 166.3 pounds. If we take a random sample of 40 men and find that the mean is 172.55 pounds with a standard deviation of 26.33 pounds, we want to test the boat company's claim. For example, what may be going on here is that the boat company wants to be able to take on more passengers. And of course, men generally weigh more than women, so the most extreme case is that each of their passengers is men. And so if they claim that the mean weight of a man is 166.3 pounds, that might allow them to squeeze on an extra passenger and still meet some regulations on weight. So let's follow the same or similar steps, I should say, as we go through and test this claim about the mean weight of men. So first of all, we want to identify the claim in terms of mathematical symbols. So we're saying the claim is the mean weight of men is 166.3 pounds, so we write that as mean equals 166.3. Step 2, just as before, will be the opposite of this claim, and in this case, the opposite of equals is not equals. So the opposite will be the mean does not equal 166.3. Step 3, the null hypothesis is going to be the one that contains an equal sign, and the alternative hypothesis will be the other one. So since the alternative hypothesis is a not equals, just as before, this is going to be a two-tailed test. The significance level is 0.05 because it's not given to us. We're assuming 0.05 since that is the most common significance level. Now here we want to calculate the test statistic using that formula we just saw. So we can do that by plugging in our sample mean, which we get from 172.55, minus the population mean that we're getting from the null hypothesis, divided by the standard deviation in our sample, 26.33, divided by the square root of our sample size, 40. So plugging all this into the calculator, I get 1.501 as our test statistic. So the next step is going to be to actually find the p-value associated with this test statistic. there's a little more to this. If you recall using the t-distribution table before, we'll be doing the same thing here, needing to calculate the degrees of freedom based on our sample size. So step 6, we're going to calculate this p-value using the student t-distribution table. However, you need to keep in mind we don't need to find the exact p-value, and we won't be able to with this t-distribution table. However, we simply need to know if it's greater than or less than our significance level, which we will be able to find out from our t-distribution table. If you want to know the exact p-value for any of the problems you encounter on the homework, you need to use some kind of technology. And so you can take a look at this week's Excel project for a way to get Excel to calculate the exact p-value for a test statistic. Since our test is two tails because our alternative hypothesis had a not equal to sign in it, and our test statistic is positive, we want to find the area to the right of our test statistic, and then since it's two tails, we're going to double it. If our test statistic was negative, because this is two tails, we want to find the area to the left of that negative test statistic and then double that. But again, in this case, our was positive. So let's look at this t-distribution table, and to save space, I cut out a little of my table. But we need to find the degrees of freedom. So if you recall, the sample size was 40. Our degrees of freedom then, what we're using in this course is n-1, which is a conservative estimate of the degrees of freedom. So we're going to look at the 39 row for our degrees of freedom. That means we're going to get our p-value, or an estimate of our p-value, from somewhere in this row 39. So our test statistic was somewhere between 1.685 and 1.304. So in other words, we just needed to find where our test statistic lies between in any of these cases. And it could be further to the right. In other words, it could be less than 1.034, or it could be greater than 2.708. In any case, find where it lies in relation to the rest of the numbers in this row. That tells you that your p-value will be between the two probabilities up at the top of that column. So you have to keep in mind, since we're talking about area and two tails, we're talking about a two-tail test rather, we're going to be in this area of two tails row. If this was a right tail or a left tail test, we would be talking about the area in one tail. So our p-value is somewhere between 0.1 and 0.2. Now, of course, we can't get any more specific than that. However, we don't need to, because if you notice, 0.1 is as small as our p-value could be, which is itself bigger than our significance level. So we have that the p-value is between 0.1 and 0.2. And think, since that is greater than our significance level, which was 0.05, we're going to be able to reject the null hypothesis in step 7. So again, since we know our p-value is greater than 0.10, because it can't be less than that, it's somewhere between 0.1 and 0.2, so our p-value is greater than 0.1, we know it has to be greater than our significance level, so we fail to reject the null hypothesis. So our interpretation is that since our claim was that the mean equaled 1.663, this was also the null hypothesis which we failed to reject, so we don't have sufficient evidence to reject the claim that the mean weight of men is 166.3 pounds. So even though our sample mean came up with a mean greater than 166.3, it wasn't large enough to cause us to say that the population of men in general must have a mean weight greater than 166.3. So we can't reject this boat company's claim based on this sample. Let's look at another example using the p-value method to test the claim. A simple random sample of 25 filtered 100 millimeter cigarettes is obtained. and the tar content of each cigarette is measured. The sample has a mean of 13.2 milligrams and a standard deviation of 3.7 milligrams. Use a 0.05 significance level to test the claim that filtered cigarettes have a tar level below 14.6 milligrams, which is the mean for unfiltered 100 millimeter cigarettes. So in other words, we're testing to see whether these filters are actually effective in lowering the tar content of cigarettes. So the question is, what do the results suggest about the effectiveness of the filters? Well, let's go through the same steps. Identify the claim. Our claim is that our mean tar is less than 14.6. The opposite then is that the mean is greater than or equal to 14.6. So the null hypothesis is going to come from the one that has the equal sign in it, and our alternative hypothesis will be the opposite, or the other one rather. So since our alternative hypothesis has a less than symbol, we know this is a left tail test. The significance level in this case, we're going to use 0.05, which is given. So let's calculate the test statistic next. So our sample mean was 13.2. Our population mean that we're assuming from our null hypothesis is 14.6 milligrams. Our sample standard deviation was 3.7 milligrams, and our sample size was 25 cigarettes. So throwing all this into the calculator gives us a sample statistic of negative 1.892. So now let's identify the p-value. And again, to do this, we're not going to get the exact p-value, but we'll be able to get a good enough estimate of the p-value so that we can compare it to the significance level. So looking at our t-distribution and keeping in mind that our sample size was 25, that means our degrees of freedom is going to be 24. And our test statistic, the first thing you may notice is that there are no negative numbers on here. So how do we compare a negative test statistic? Well, you can think of it in a couple different ways, but the way I'm going to think of it is change all these numbers to negative, and now think about what your test statistic is between. Or maybe a better way to do it is convert your test statistic temporarily into positive, and now compare it to all these numbers. So our positive test statistic was between 1.711 and 2.064, which tells me, and again, since this is a one-tail test, a left-tail test, I'm going to be in this area in one tail. My p-value is somewhere between 0.025 and 0.05. So my p-value is between 0.025 and 0.05, and since that means that our p-value is less than 0.05, which is our significance level, we can reject the null hypothesis. And since the original claim was that our mean was less than 14.6, and we rejected the null hypothesis that the mean equaled 14.6, it appears that we have enough evidence to support the claim that the mean tar content in the filtered cigarettes is less than the mean tar content in unfiltered cigarettes. So as far as what this suggests about the effectiveness of the filters, it appears the filters are indeed effective in reducing the amount of tar content. So let's look at a couple examples utilizing the critical value method. Take a look at this example. The U.S. Mint has a specification that pennies have a mean weight of 2.5 grams. A sample of 37 pennies manufactured after 1983 has a mean weight of 2.4947 and a standard deviation of 0.01648. We're going to use a 0.05 significance level to test the claim that this sample is from a population with a mean weight equal to 2.5. Do the pennies appear to conform to the specifications of the U.S. Mint? So just like the p-value method, we're going to have the first 5 steps be exactly the same. We're going to first of all identify the claim, and in this case the claim is that these pennies came from a population that had a mean weight of 2.5. The opposite then is that the mean does not equal 2.5, and we'll get our null and alternative hypothesis the same way we've done before. The one that has the equal sign in it will become our null hypothesis. The other one will be our alternative, and since this is a not equal sign in our alternative hypothesis, we are dealing with a two-tailed test. Significance level was given to us as 0.05, so let's calculate the test statistic. We take our sample mean, 2.4947, subtract off the claimed mean in our null hypothesis, 2.5, divide that by our sample standard deviation, 0.01648, and divide that by the square root of our sample size. We used 37 pennies in our sample size. That gets us a test statistic of negative 1.956. So now let's identify the critical value corresponding to a 0.05 significance level and 36 degrees of freedom in a two-tailed test. So a two-tailed test means that we're looking for a value that would have 0.05 in two tails. So in other words, half of this would be to the right and half of this would be in the left tail. So let's take a look at the t-distribution table and see what this means and how to identify the critical. So of course we had a sample size of 37, so our degrees of freedom will be 36 in this case, meaning we're in this row 36 here. We are dealing with a two-tailed test, so I'm going to look at this area in two tails row, and our significance level is 0.05. Now of course that means that 0.025 will be in each individual tail. So if I want to divide the significance level into the two tails and look for the critical value that has 0.025 in one of those tails, that's fine. But it's easier with this t-distribution table to, if you're dealing with a two-tailed test, just look at this row that says in two tails. So we're in the 0.05 in two tails, and we're in the 36th row. That means our critical value will be this 2.028. Since this is a two-tailed test, however, we also need to consider the negative 2.028 case. We found our critical values to be plus and minus 2.028. So in comparing this test statistic to these critical values, in general, if our test statistic is greater than the positive critical value or less than the negative critical value, then we'll reject the null hypothesis. So in this example, since our test statistic was negative 1.956, and it's not less than the negative critical value, negative 2.028, so we fail to reject the null hypothesis. If our test statistic was a positive 1.956, then we'd compare that to the positive critical value. But again, then it would not be greater than the positive test statistic, so we would still fail to reject the null hypothesis. So the claim and the null hypothesis were both that the mean equaled 2.5 grams. We did not reject that null hypothesis based on this sample, so it appears that the weight of these pennies conform to the U.S. Mint specifications.